Good afternoon, class. Hello, is it audible? Hello. Yeah, is it audible clearly? Hello.
Yes, sir.
Okay, thank you. So, in the last class, we discussed about the propagation of the parallel polarized plane wave through the dielectric interface, and we have seen that when for the p polarized light, through the dielectric interface. So we have taken this dielectric interface along xy plane. This is the plane of incidence is along the xz. This was the plane of incident plane wave. Okay, Ki. This was the reflected one, Kr, and this is the transmitted one, Kt, propagation vectors. And this was the angle of incidence theta I. This is also theta I, and this is theta t. And since we are considered about the p polarized light, so the electric field will be in the plane of incidence, that is either x direction or either g direction, and we have considered that magnetic field is along the y direction. So according to that, electric field was at along this direction EI, and this will make the angle with the x-axis theta I. Okay. And then similarly, we can decompose it. So this is the EI cos theta I. And similarly, in this case, for the reflected case, the electric field was along the downward direction, along this direction. And with the x-axis, it was making angle theta I. So this component was, this is ER cos theta I. And in the case of the transmitted wave, the electric field was again along the upward direction, perpendicular to the Kt. This was the AT, and it was making the angle with the x-axis theta t, and the component of the transmitted wave along the x direction was Et cos theta t. So with this information, we have derived the reflection coefficient and transmission coefficient in terms of the intrinsic impedance and the medium 1 and medium 2. So the reflection coefficient we have calculated. Reflection coefficient for the parallel polarized light, it is given by R parallel or gamma parallel. Okay, and this was equal to reflected amplitude, electric field amplitude divided by incident electric field amplitude, and this was equal to eta 1 cos theta I. So this was the eta 1 cos theta I minus eta 2 cos theta t. Then this is divided by the same parameters, same quantity with the plus sign. So this is eta 1 cos theta I plus eta 2 cos theta t. Okay, so this was the reflection coefficient for the parallel polarized light we have derived, and also we can write for the transmission coefficient. That is the tau parallel. It is equal to transmitted amplitude of electric field divided by the incident electric field amplitude, and this is equal to 2 times eta 2 cos theta I divided by same denominator which was in the case of the reflection coefficient, and it can be written as eta 1 cos theta I plus eta 2 cos theta t. Okay, so this was the reflection transmission coefficient in terms of the intrinsic impedance of the medium 1 and medium 2, and the angle of incident and angle of transmission or reflection. Okay, for the parallel polarized light. So can anyone can write this reflection coefficient and transmission coefficient in terms of the reflective index of the medium 1 and medium 2? So kindly write in terms of the reflective index, reflection coefficients. Okay, so for the medium 1 it is n1, and for the medium 2 it is n2, and let me know the answer. So did you get the reflection coefficient in terms of the reflective index? Anybody? Anudeep?
Sir, is eta is equal to 1 by root epsilon? Is that correct, sir?
Eta is equal
Eta is
to?
by root of mu by epsilon. And
Yes.
we have n1 is equal to root of epsilon. So can we write eta is equal to 1 by root n?
Eta is equal to 1 upon root n. No.
Sir, eta 1 is equal to 1 by root n1, or eta 2 is equal to 1 by root n2. Can we write like that, sir?
I think there should be no root under root. Just check it once again.
Yes, sir. One second, sir.
Sir, if the final equation have n2 in the place of eta 1 and n1 in the place of eta 2, like that.
Yeah, that is true, but how it will come?
Applying the previous equation, and the root of eta, root of mu 0 epsilon 0 will be cancelled out, and 1 by 1 and 1 by n2 will remain.
So what was the relation between the reflective index and the impedance? So for example,
Eta is equal to
yeah, eta 1 is equal to
1 by n1
1
root
by n
mu
1
0 by x10.
root mu 0 from epsilon 0. This one? This one you are telling?
Yes, yes. Yes, sir.
Yeah. Yes. So yes, this is correct. There is no under root n1. Someone was telling that under root n1. So this is the relation. Similarly, we can write for the n2. It will be effectiveness 1 upon n2 mu naught epsilon naught. We need to put it right. So as you said correctly that in the place of the eta 1, you will get the n2, and in the place of the eta 2, you will get the n1. Okay, by just solving this. So we can write these equations in terms of the refractive index, and this will be equal to, I'm going to write here. So this will be n2 cos theta I minus n1 cos theta t divided by n2 cos theta I plus n1 cos theta t, right? Is it okay? Hello.
Yes, sir.
And similarly, we can write for the transmission coefficient, and this will be equal to the 2 n2 and theta 2 will be n1 cos theta I divided by n2 cos theta I plus n1 cos theta t. Okay, so this is in terms of the defective index. And this was in terms of the impedance. Okay, so this was the relation for the reflection coefficient in the both the cases for the impedance and the reflective index, because some cases the problem is asked when the reflective index is given, and sometimes it is given in terms of the impedance. So we need to know both the relations. Now further we can solve this, and we can simplify this reflection coefficient and transmission coefficient. So let us take this one, reflection coefficient in terms of the reflective index, and this one. And let us see if we can further simplify this. Can we write gamma parallel is equal to n2 cos theta I minus n1 cos theta t divided by n2 cos theta I plus n1 cos theta t. This is equal to the 10 theta I minus theta t divided by 10 theta I plus theta t. So can you derive from this to this?
Sir, we can't see the top portion, sir.
Is it okay now?
Yes, sir. Thank you.
So we need to derive from this to the in terms of the tangential. So how we need to start? Can anybody can have any clue? So I'm going to do this one. So we know that we need to apply here. We know that here there is no refractive index. Only refractive index is coming in this one. So we need to remove the refractive index. So for that we need to use the Snell's law. We know that Snell's law for the diffraction. It is given by n1 sine theta I is equal to n2 sine theta t, and from this we can write sine theta I upon sine theta t is equal to n2 upon n1. Okay, so now let us see these equations. So gamma parallel we can write this, we can write when we take the common the refractive index. So it will be n2 upon n1 cos theta I minus cos theta t divided by n2 upon n1 cos theta I plus cos theta t. Okay, and we can write this n2 upon n1 is equal to sin theta I upon sin theta t. So sin theta I upon sin theta t into cos theta I minus cos theta t divided by sin theta I upon sin theta t cos theta I plus cos theta t. Okay, now just we need to solve it in the numerator and denominator, and further we can write in the simplified version this is equal to the sin theta I cos theta I sin theta I cos theta I minus cos theta t sin theta t sin theta t divided by sin theta I cos theta I plus cos theta t sin theta t. Okay, now we can apply some trigonometric identity. The trigonometric identity we can write that we know that 2 sin theta is equal to 2 sin theta is equal to what is that? Sin 2 theta is equal to, sorry, sin 2 theta is equal to 2 sin theta into cos theta. So this trigonometry we can see that here. So sin theta cos theta is equal to sin 2 theta by 2. So from there we can write this is equal to sin 2 theta I divided by 2 minus sin 2 theta t divided by 2 divided by sin 2 theta I divided by 2 plus sin 2 theta t divided by 2. So 2 will cancel out from both the numerator and denominator, and further we can write this is equal to sin 2 theta I minus sine 2 theta t. This is equal to sine 2 theta I plus sine 2 theta t. Okay. Now again we need to apply the another trigonometric identity, and this is equal to the, so we know that this can be written as, here this is sine c minus sine d, and here it is sine c plus sine d. Okay, so what is the sine c minus sine d? What is that identity? Anybody? So identity sine c minus sine d. What is this equal to? So basically this is equal to 2 cos c plus d by 2. Okay, into sine c minus d by 2. Okay, and in the case of this is the numerator, in the denominator it is plus sign, so sine c plus sine d is equal to 2 sine c plus d by 2 into cos c minus d by 2. So we need to use this trigonometric identity here and here, and then we can solve this. So from this we can write the gamma parallel is equal to, so it will be, can be written as 2 cos c plus d by 2, 2 theta I plus 2 theta t, 2 theta I plus 2 theta t divided by 2 into sine 2 theta I minus 2 theta t divided by 2 in the denominator. So maybe we can write 2 sine 2 theta I plus 2 theta t divided by 2. Okay, and then this is, here we can write this is the cosine one, 2 theta I minus 2 theta t divided by 2. So this 2 is in the angle also will cancel out all the 2, and this 2 will also be cancelled out from the numerator and the denominator. So finally we can write this is equal to cosine of theta I plus theta t into sine of theta I minus theta t. This is divided by sine of theta I plus theta t into cosine of theta I minus theta t. Okay, and then from here we can write that this gamma parallel is equal to the, so this sine theta I minus sine cos theta I minus theta t will be 10 theta I minus 10 theta t, 10 theta I minus 10 theta t, and this will be in the denominator, so it will be 10 theta I plus 10 theta t divided by 10 plus theta plus 10 theta t. So in in this way, we have derived, further we can simplify the reflection coefficient for the parallel polarized light in terms of the tangential and angle of difference between the angle of incidence of and transmission, and here the addition of the angle of incidence and the angle of reflection or transmitted plane wave. There is no refractive index, there is no impedance in this form. Okay. Some coefficient. Okay. So similarly, can anybody write? One can simplify for the parallel for the transmitted coefficient that is not in terms of the refractive index, but there is no refractive index and there is no impedance in that relations. So try to solve that and tell me the expression. So basically we can see that we know that. So let me erase this first. So parallel, the transmitted coefficient for the parallel light will be top is equal to 2, it is equal to the 2n1 cos theta I divided by n1 cos theta t plus n2 cos theta I. Okay. Now again we need to write in terms of the Snell's law we can write. Okay. So from here we can write this is equal to the 2 cos theta I divided by cos theta t plus n2 upon n1 cos theta I, and then 2 upon n1 again we know that this is equal to sin theta I upon sin theta t. This is, so we can put it there. So this is equal to 2 cos theta I cos theta t plus sin theta I upon sin theta t cosine of theta I. Okay. And then further we can simplify this in terms of the numerator and denominator, and we can write that this is equal to 2 sin theta t cos theta I divided by sin theta t cos theta t plus sin theta I cos theta I. Okay. And further we can write this can be written in terms of the sin 2 theta. Okay, so this is equal to 2 sin theta t cos theta I, and this is equal to the sin 2 theta t divided by 2 plus sin 2 theta I divided by 2. So we can use the trigonometric identities. Okay. And then further, this 2 will be cancelled out from the numerator and denominator. And then this can be equal to sin theta t cos theta I divided by sin 2 theta t plus sin 2 theta I. And then we can apply the sin c plus sin d trigonometric identity here. Okay, so we can write again sin c plus sin d will be sorry, this here it will be 2 and here it will be 1/2. It will not be cancelled out. So sin c plus sin d can be written as 2 sin theta t cos theta I divided by this is equal to the sin c plus d by 2. So sin theta I plus theta t sin theta I plus theta t and cosine of theta I minus theta t. So this is the tau parallel transmission coefficient where there is no effective index and there is no impedance, and also in the simplified version of the parallel polarized light. Okay, transmission coefficient. Okay, so we can make a conclusion. So what will happen to the electric field of the transmitted wave and the reflected wave and the incident wave? Okay, so we know that again from this transmission coefficient for the parallel polarized light, we can make two conclusions. That the transmission coefficient that is for the parallel polarized light could be greater or less than the unity, because this quantity is 2 times of this, so we get to be greater or less than unity. Unity means if you are comparing with the incident field. Okay, and there is, so what is the meaning of this? That means we can say that the transmitted electric field would be greater or less than the incident electric field. So similar conclusion we have made in the case of the parallel polarized light, right? If you remember. Similarly, we are also getting for the parallel polarized light, the transmission electric field may be greater or less than the incident electric field, and the condition we know. Similarly, as we have done in the case of the parallel perpendicular polarized light, the condition we have derived, similar condition also we are getting in this case for the parallel polarized light. And we can also make the conclusion for the reflected light for the parallel polarized light. And we can see that if you remember the expression for the this gamma parallel. So we can see that this magnitude of the reflection coefficient, magnitude of deflection coefficient gamma parallel is always less than unity. Okay, and there is a phase difference of 0 or pi between the incident and the reflected wave. So that's the conclusion from the when the reflected parallel polarized light is passes through the dielectric interface. So in this is the conclusion we have made from this expression. So if anybody has any question, so they can ask. Any doubt in this topic for the parallel polarization of the plane wave through the dielectric interface?
Sir,
Yeah,
sir, when we say that the transmitted electric field could be greater or less than the incident field, do we mean the amplitude or anything?
amplitude.
Sir, if amplitude increases, then the energy, will it also increase?
Uh, Not necessary, because energy is not directly proportional to the electric field. Energy depends upon the magnetic field also. So as we can see, we have discussed in the last case for the perpendicular polarization, the conservation of the power, that is the energy basically. So energy is conserved. Energy could not be greater than the incident wave, either for the reflected or transmitted wave. Because again, if the transmitted electric field is getting greater than the incident electric field, so at the same time, the magnetic field will be lesser to make it equilibrium condition or the conservations of the energy or power. Okay. So like reflectance and transmittance always will be the equal to 1 summation of this, but not in the case of the coefficients. Okay.
Yes, sir. Thank you.
Anybody else? If there's no questions, so let's see you in the next class. Thank you.